Right. So this illustrates some things that I've already talked a little bit about. But here, if we were to plot an infinitely large population and we're plotting IQ, the mean of this distribution would be right smack in the middle, and we would call that mean mu. We would use the Greek symbol because we're talking about an entire population, right? And so an infinitely large population. So whenever you're talking about populations and you're plotting any kind of statistic, like here we're plotting an average, a mean, you have to use the Greek symbol. This is a parameter, all right? And just as a rule of thumb here, you might want to write this down. As a rule of thumb, anytime we're talking about a hypothetical distribution, we always use the parameters, okay? We use the Greek symbols, all right, for parameters, always, when we're talking about hypothetical distributions. Okay, so if we're looking at IQ scores in this infinitely large population, we see the general trend that for the most part, the most frequent IQ score is 100. And we actually believe that that's pretty much true, all right, because we have now administered IQ tests to I don't know how many people, but a lot, right? A lot of people have had their IQ measured. And the mean of all those IQ scores is really right around 100. So we don't know what it is in the population for sure, but our best guess is that it is the mean of the population, and which means it's also the mode, the most frequent score, and it's the median, the score that separates or splits the distribution in half. All right, so that if you had a gazillion, bazillion scores on this side, you would have the same number on that side. Okay, so 100 goes here. Here's something new. This is referred to as a tail. So here, this is the middle of the distribution. What we can say is that as IQ scores drop, so does frequency, right? Frequency is dropping. And when we get into the tail of the distribution, that's where we see the lowest frequencies of all. So there would also be a tail on this side, right? So as frequency goes down, when we get into the tail, we would call this the positive tail. This would be the negative tail. When we get into the positive tail, again, the frequency is very low. So what we can say about tails in general is that anything in the tail is a very low frequency score, right? Or category, low frequency. And if it's low frequency, it means that they don't happen all the time, right? Which means their probability of occurrence is also very low. So these are low probability events. Here, because we're in the middle, these events are the most common, or in this case, the events are IQ scores. Whatever these frequencies are, they happen the most often. So we could say if you are in the middle of the distribution, these are the most probable scores, right? So do you see that there is a relationship between frequency and probability? High frequency scores happen a lot, so we can say they are high probable events, high probability of occurring. Whereas anything out in the tails is infrequent, so those are not probable. They are unlikely events. So now we can say that as we increase scores from the middle, okay, if we start at the middle, and as the scores on the x-axis increase, frequency goes down and probability goes down. Same thing in this direction. Here, if we start in the middle, as scores decrease, all right, frequency goes down, and so does their probability. Right. what makes normal distributions so special? Well, for one, it gives us understanding of what it means to be normally distributed. So a lot of researchers, they may collect data, and remember, if you're collecting data as a researcher, in all likelihood, you are collecting data from a sample, right? It's highly unlikely that you would have a population and you were able to get everybody in that population. You would have had to have defined your population with so many criteria that there were very, very, very few people that made up your population. If you only have 10 people in your population, then yeah, there's a good chance you could get all 10. But 99.999% of the time, I'm estimating, of course, but the vast majority of time, we're looking at samples. And samples, if you were to plot the frequency of every score in your sample, it very well might resemble, whoops, no, don't come up yet. It might resemble this basic shape. It's not going to look perfect, but it might have just, it looks something like this, all right? And so if I'm that researcher, I might communicate with another researcher and say, my sample data was normally distributed. And right away, that other researcher is going to have this image in his or her head. And so they understand what I'm talking about when I say my data was normally distributed. All right, so as statisticians or as researchers who use stats, we want to develop a common language so that we know exactly what the other person is referring to. Okay, it's kind of like doctors, right? Doctors have their own medical jargon, and all doctors learn the medical jargon. And when they're speaking to each other, they know exactly what the other person is referring to because they have this common jargon. Well, same thing in statistics. We're going to have a common set of jargon. And we're going to know what we're talking about when we talk to one another because we understand the jargon. So now you should understand if a researcher says, my data was normally distributed, what they're talking about is this basic shape, okay? Where again, the variable of interest is down here, and the line just tells you the relative frequency of each particular category, right? Only if we're talking about actual data, they're talking about actual data, they can plot it. They can actually have a y-axis here with numbers. And you'll see, though, that when that happens, you're not going to get this perfect shape, and you will not see this very flowing line, okay? But again, it gives us shared jargon that we can use to talk with one another. Second reason why the normal distribution is so special is because, and again, remember, there's actually an infinite number of normal distributions, but they are the foundation on which inferential statistics are based. Now, remember what inferential statistics are. These are statistics that we calculate on sample data, and those statistics tell us something about the population that the sample came from. All right? And so in order to understand inferential statistics and how they do what they do, you have to have an understanding of this normal distribution. So I'm not going to elaborate right now on this. Remember, baby steps. There's certain things we have to do before we can go into more advanced topics. You don't get somebody in grade 1, who's just learning to read, you don't hand them Shakespeare. Actually, I still struggle with Shakespeare. I never really did get how Shakespeare wrote. But, we start with them singing the letters of the alphabet, and then we teach them what each letter looks like. And we teach them the difference between a capital and a lowercase, so uppercase, lowercase letters, and then the sounds that they make. And then we move into blends like ch and sh. And finally, we teach them words and how words make sentences and sentences make paragraphs. You see where I'm going with this, right? So you're going to have to learn a lot of foundational stuff before we begin to put it all together. It does come together. It just, we're going to do that later in the course after you've got all the basics, okay?